Hi, my name is Rachel Martin, and this is my Lab 9 Part 1 at-home physics lab. The purpose of Lab 9 is to model a spring moving in two dimensions and comparing it to experimental values found from a video clip provided. The lab also asks us to analyze the spring's potential energy. The main principles utilized in writing the code included the momentum principle and the energy principle. The momentum principle is applied to determine the net forces, while the energy principle is used to determine the spring potential energy, gravitational potential energy, and kinetic energy. I used Tracker to analyze the position of the mass with respect to time. I set the axis at the fixed attachment point with positive x to the right and positive y facing up. I then used the calibration stick to record the given distance from the origin. I then plotted each mass point which recorded position and time. I extracted this position data and saved it as a .csv file for my computational model to reference. To create the computational model, I first edited the initial conditions. I set the ball's mass equal to 0.402 kilograms, which is given by the problem. I set the ball's initial position to the values given by Tracker, and the ball's initial velocity was 0 because it started at rest. I then set the gravitational constant equal to 9.81, and I found the spring constant using Hooke's law. And then I found the initial stretch based on my Tracker data. I edited my potential energy due to gravity, doing ball's mass times gravity times the ball's position or its height. I set delta t equal to 110.5 because that was the time for each time frame. I set the time to be less than 9.5, which I found from Tracker. I then edited L to equal the ball's position minus the spring's position, L hat to equal L divided by the magnitude of L, and the stretch equal to the magnitude of L minus L initial. And then I added Hooke's law. The force of the spring equals negative Ks times L hat, so it wouldn't be a vector. I then changed F net to equal F spring plus F gravity. And I changed the ball's velocity using the momentum principle. I updated the ball's position and determined how to find the final velocity and initial velocity, and I set the initial velocity equal to ball.v initial. I changed p initial to equal the ball's mass times the initial velocity, and p final to equal the ball's mass times final velocity. Changed delta v to equal final velocity minus initial velocity, and changed the momentum to equal final velocity minus initial velocity, which is important for the change in momentum with respect to change in time, which will give us F net. I edited p hat to equal p initial divided by the magnitude of p, magnitude of dp dt, the parallel component of that, to equal the magnitude of p final minus the magnitude of p initial divided by delta t. I edited dp dt parallel to equal the magnitude of dp dt times parallel times p hat. And F net parallel is equal to dp dt parallel. Okay, and now I'll run it. I then used the energy principle to update the change in the spring potential energy due to work. Here this is. And it's plotting the change in potential energy based on the spring versus time. Now I'll compare the Tracker data to the VPython data. The period is the amount of time it takes for one oscillation to happen. I looked at two peaks on each graph in the computational model and in Tracker and determined the change in time, which is the period. The values differed between the computational model and experimental findings for both oscillations in the x and y directions. Okay, now for the what does it mean questions. The first question asks to compare the period of oscillation dealing with the x component of position and the y component of position, and if they differ. Yes, the period of oscillation for the x component is greater in magnitude than the period of oscillation for the y component. They differ because Dr. Greco stretched the spring more in the x direction than in the y direction. The second question asks for the work done by the surroundings and whether or not the energy principle was satisfied. No work is done on the spring by the surroundings, therefore the change in energy of the system is zero and the work done is zero, so the energy principle is satisfied. The third question asks about redefining the origin. Instead of the origin being where the spring's attached, it's now where the mass hangs. The question's asking whether or not this would change the three plots for the system's energy, and also whether the physics of the system would change. The physics of the system would not change because the principles applied wouldn't change. At first, it seems that the gravitational potential energy might change, but it doesn't. The same principles are applied, but the height component of gravitational potential energy would have to be redefined. The plots for spring potential energy and kinetic energy would also stay the same because no work or energy is actually changing in the system.